Hey there, AP Chemistry. Welcome to the last couple concepts in bonding. We're going to talk about the VSEPR model, also known as VSEPR. I know it doesn't actually spell VSEPR, but it's better to say VSEPR than VSEPR. So the VSEPR model, hybridization and magnetism. So these are the last couple concepts we're going to talk about relative to bonding. Basically, between chemistry and what we just talked about in chapter 8, you have the bulk of bonding. And now what we're going to do is talk about how orbitals, atomic orbitals, and these theories that we've been talking about all along the way, how those change when you take two atoms and actually bond them together. So let's dig in. All right, so one of the last models we talked about was the localized electron model, also known as the Lewis structure model. And when we look at Lewis structure and when we use Lewis structure, basically we are talking about a couple different possible structures and the connectivity that happens within the molecule. So when covalent bonds formed, what is actually connected to what, and how are the electrons distributed between those things, between those atoms? That's really what a Lewis dot structure communicates. But what a Lewis structure lacks is the geometry of it all. Okay, we can tell by looking at something like methane that methane has 4 hydrogens and they are bonded to the carbon, right? That's kind of what we determine when we look at the Lewis structure of methane. Or if we're looking at carbon dioxide, we can look at how those oxygens are both bonded to the carbon. We can see that the carbon is bonded to 2 oxygens. It's bonded with a double bond, which we know is going to be shorter. When we look at methane, we can see that the 4 hydrogens are bonded on with single bonds, so those are going to be longer. We can also see when we are looking at carbon dioxide that there's a couple lone pairs of electrons that are distributed around those electrons. So we can get a lot of information out of a Lewis structure, but what we can't get out is geometry. Are those oxygens bonded to the carbon at right angles? Are those oxygens bonded to the carbon at 180-degree angles? What are the angles inside methane? The way I drew it, it looks like a 90-degree angle. So the geometry of a molecule is where we're going to go into, and that's what the VSEPR model indicates. The VSEPR model tells us what the geometry of those bonds are, and that becomes really important when we start looking at the interaction of these molecules. If you're trying to design a drug to target a cancer cell, one of the main components of design is going to be what that drug can migrate through, what that drug can dissolve into, what that drug can attach itself to, and all of that is determined by shape. So this VSEPR model is going to help us begin to think about possible shapes that these molecules can take on. It's going to show us a 3-dimensional arrangement, which gets a little bit tricky because we're going to be drawing this on a 2-dimensional plane. So we'll talk about how we do that. And VSEPR stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. Okay, so that's what VSEPR stands for. And so the title of this model gives us an indication on what is the driving force behind the geometry. And the driving force behind the geometry is going to be electron pair repulsion. Electrons that we find in a valence shell, so we're not talking about core electrons here, we're talking about valence shell electrons. And those electron pairs inside the valence shell are going to repel each other. And when they repel each other, they repel each other into very predictable shapes. And those very predictable shapes that are caused by this electron repulsion is what we are going to talk about and discuss how to predict those shapes. Okay, so the shape or the geometry of these molecules, it's determined, it's driven, the shape is caused by the driving force of electron pair repulsion, and it's determined by bond angles. So when we describe the shape, we're always going to talk about an angle, and then also bond length. And this bond length gets back to the Lewis dot structure, where we talk about the single versus double versus triple bond being long, shorter, shortest. Okay, so those are the two considerations we're going to make within this model. All right. Like I said, as we look at this model, we're going to talk about how the electrons repel each other, and that's going to be the driving force behind the geometry that occurs. Okay, so there's a couple rules behind this. When we're looking at something like, let me see if I can come up with something that combines all of them. All right, let's just look at something simple like ammonia. Okay, so ammonia has single bonds, and it also has a lone pair. So one of the rules is that this lone pair of electrons that contains 2 electrons, and this bonding pair of electrons that contains 2 electrons, they don't take up the same amount of space. Because these localized electrons that are localized between the nitrogen and the hydrogen, because those are being shared between 2 atoms, they actually are going to take up a smaller amount of space. Because these 2 electrons that are found on nitrogen, they're not actually shared to anything. They're going to take up a bigger amount of space. So when we're looking at electron pairs that are repelling each other, 2 bonding pairs repelling each other are going to be at a different angle than a bonding pair and a lone pair repelling each other. That lone pair is going to take up more space. When we're looking at bonds themselves, multiple bonds and single bonds, they take up the same amount of space. So if we look at, I can't come up with one that kind of contains all of it, but if we go back to ammonia versus carbon dioxide, okay, and we look at the central atom. So the central atom for this is nitrogen. The central atom for this is carbon. What we're looking for is electron pairs that repel each other. Okay, now nitrogen and carbon are in different scenarios for a couple different reasons. First of all, this carbon has a double bond on one side and a double bond on the other side. Double bonds are going to repel just like single bonds. So these double bonds on one side, they are going to operate as a unit, repelling anything else that's around this carbon, which would be this other double bond. So really, when we look at carbon, we have 2 areas of electrons that are repelling each other. Even though those 2 areas of electrons actually contain 4 electrons each, we still only have 2 areas. If we look at nitrogen, we want to determine the same thing. Nitrogen's our central atom here. How many different areas of electrons are around that nitrogen that could repel each other? So let's look at this. Nitrogen has a single bond here, so that's 1 area of electrons. Here's another single bond, another area that's going to repel. Here's another single bond, another area that's going to repel, and here's a double bond, a final area that's going to repel. So this nitrogen actually has 4 areas of electrons that are going to repel each other. Okay, so this is rule number 2. Single bonds count as an area. So do double bonds. So do triple bonds. So do lone pairs. So even though they contain different amounts of electrons, because they're locked into that one area, they still count as one repelling region around that central atom. If you do have an unshared pair, which would be a lone pair, or you have multiple bonds, double or triple, they're going to count as one effective region, one area that repels, but they're going to distort the shape. So lone pairs count as one repelling region, but they're going to take up more space than a single bond. Okay, same thing with like double and triple bonds. And we'll talk in a little bit about how double and triple bonds distort the shape or change the shape or lock in the shape. We'll talk about that in a little bit. But just know they do count as one repelling region, but they don't all take up the exact same amount of space. The amount of space they're going to take up is just going to be slightly different from each other. Okay, so that's kind of the theory. Tuck those rules in the back pocket. They might not make a whole lot of sense yet, but let's walk through this and then they'll make more sense. All right, so basically the shape comes down to how many repelling regions are around the central atom. So when you look at something like those molecules we've been talking about all along, carbon dioxide, okay? That was supposed to be 2 dots. The first thing we want to determine is how many effective pairs, how many effective regions are around the central atom. Okay, so here's my central atom, carbon. Carbon's my central atom. So how many different regions are around the central atom? 2. Now, what shape will this be in? So if I have 2 regions that repel each other, what shape is it going to force itself into? Okay, so to help us with this discussion, I have balloons, because balloons repel each other a lot like electrons do. Okay, so we're going to take our balloons, we're going to tie them together, and the balloons are going to push away from each other and fall into a shape that's similar to what molecules fall into when they have electrons that repel each other. So here we go. 2 regions. I'm going to tie them together, so the knot in the middle is going to be my central atom. Wait for it. This is my little party trick. I'm very popular with little kids at birthday parties that have balloons because I do this for them. They just don't know that I'm teaching them chemistry. Okay, so if I have 2 balloons, let me move this back so you can see what I'm doing. All right, 2 balloons. They're gonna repel away from each other. What kind of shape do they naturally fall into? And you can see if this knot is my central atom, okay, the balloons are going to be the areas of electrons that are repelling each other, and then the oxygens would be at the ends of the balloons, okay? This is going to be a 180 degree molecule. So the way that I actually have it written right now as a Lewis dot diagram, where my 2 areas are directly away from each other, okay, at a 180 degree angle, that's going to be my molecule. So we call this a linear molecule. And anytime you have a central atom attached to 2 other things with your electrons repelling here, you're going to get 180 degrees, and we're going to call this a linear molecule. So pretty straightforward, right? What's going to happen when I add a 3rd balloon in here? Okay, so take a minute, write down a prediction. What is the shape going to look like, and what's going to be the angle of your bond? See if you can predict that while I try and tie this balloon up. All right, do you have it? Here we go. Here's our structure. Okay, so what angle is that at? 360 would be a full circle. All right, so what I have is I have my central atom here, and I have 3 repelling regions. 1, 2, 3. So I'm going to have something attached out here, right? What's this angle going to be? It's going to be 120 degrees. So with 2 effective pairs or 2 repelling regions, I'm going to get 180 degrees. It's a linear molecule. With 3 effective pairs or 3 repelling regions of electrons, I'm going to get 120 degrees. And we call this trigonal because it's 3, right? Like a triangle. Notice if we connect the dots, it makes a triangle. So it's going to be trigonal planar. Because notice all 3 are in the same plane with each other. All in the same plane. Trigonal planar. A good example of this would be something like BF3. If you draw this one, remember BF3 is one of the exceptions to our Lewis dot diagram. That boron's not going to have a full octet, which is okay for boron. And the formal charge actually comes out to support this. Okay, but because it only has 3 effective regions around it, each of these angles is going to be at 120 degrees. Okay, let's do 4. So see if you can predict. I'm going to attach a 4th balloon in here. What is the angle between all of the balloons going to be? All right, I'm going to move this even farther back so you can see this. Okay. And if you said 90 degrees, you are wrong. Okay? I can force it into 90 degrees, but this is not as far as the balloons can possibly get away from each other. Notice I do have 90 degrees in a plane, but this is a high energy system, and watch what happens when I exert some force onto the system. It's actually going to fall into a lower energy system. Let's see if I can get this on the camera. There you go. I just shook it just a little bit, and the balloons fell into a more stable, lower energy arrangement. Okay, so this one's kind of weird. So notice, let me try and orient you. If I get the yellow and the white into a plane, okay, so the yellow's going up, white's going down at an angle, but they're in a plane. Notice that the pink is coming out at you, and there's actually a purple one you can see here on the bottom that's actually going back into the plane. Okay, so this is what we call a tetrahedral arrangement. So this is going to happen with anything that has 4 effective regions around it. So 4 regions of electrons repelling. And this is actually one of the most common organizations because we have so many molecules that are carbon-based, and carbon tends to form compounds that have 4 connections. Okay, this is one of the most common things, common arrangements. So we call this tetrahedral. Here we come across that tetra prefix again. Remember, tetra means 4. We saw that in covalent bonding. We also see it in the game Tetris, in which everything has 4 shapes. Now the question is, so we have a ton of different examples of this. Let me erase this, and so I can draw out some of these examples. So this is 4. This is a tetrahedral tetrahedral arrangement. And we have a lot of examples. CF4 is an example. So notice when I draw methane, I have 4 regions of electrons that are going to repel each other. Same thing with ammonia. When I draw ammonia, I have 4 different regions of electrons, 3 single bonds and a lone pair that are going to repel each other. Same thing with water. When I draw water, I'm going to get 4 regions around oxygen that repel each other, 2 single bonds and 2 lone pairs. So all of these have 4 regions of electrons that repel each other around whatever is central. Now, a tetrahedral is not going to be a 90-degree angle. Remember, a 90-degree angle is what's going to form when we force them to be closer than they want to be. Okay, so whatever our angle is going to be has to be greater than 90 degrees. You're going to have your central atom. If I have one going up in the plane and one going down in the plane, okay, that would be, again, I think I had it yellow and white. So yellow's going up in the plane, white's going down at an angle in the plane, right? Pink's going to come out at you, purple's going to go back away. So the pink, to draw it coming out at you, we draw it as like a triangle. It's like that line is getting bigger as it comes out. And the purple we draw kind of getting smaller in the back. And this angle is actually going to be 109.5 degrees. And yes, you do have to know that angle. It's one of the weirder ones, but don't worry, there's not too many of those that you actually have to remember. So tetrahedral is going to be 109.5. Now, notice the 3 examples that I've drawn, methane, ammonia, and water, they're not all equal, right? So methane has 4 single bonds. Ammonia has 3 single bonds and 1 lone pair. Water has 2 single bonds and 2 lone pairs, right? So they're actually not all going to be 109.5. Methane will. Methane's kind of our true example. We have the 4 single bonds. Nothing else is weird. No double bonds, no triple bonds, no lone pairs, right? So methane is actually going to be 109.5. Ammonia is going to have this lone pair at the top that's bigger than the rest of them. It takes up more space than the rest of them. So let's say this yellow was a lone pair. What it would do is it would actually force the other 3 down away from it a little farther. So these bonds in ammonia are actually going to be smaller than 109.5. Now, if that's all you can tell me, that's enough for the test. The test doesn't actually require you to know the exact value of that bond. If you want to know the exact value, it's actually 107 degrees. But as long as you can tell me that it's less than 109.5, you're in good hands. Now, for water, both of these would actually take up more space. So it's like both of these took up more space. What would happen to the 2 that are remaining is they would get very squeezed together. So here's the orientation. Let's see. Let me give you, here's the orientation I showed you before, right? Okay, it's like these squeeze apart. And oftentimes we actually draw water. Let me rotate this for you, like this. We draw water like this. We draw water like this. We show the hydrogens in a plane with each other, and then they get squeezed. Actually, this one might be 107 degrees. I think it is. I don't think ammonia is 107. I think water is 107 degrees. They're going to, again, if you can tell me that it's less than 109.5, that's actually what you need to be able to tell me for the test. And water is such a common molecule. It is a tetrahedral shape, but because it has those 2 lone pairs that kind of push the bonding pairs close to each other, sometimes you see that it's given a different name, and we call it a bent molecule. It's just the two bonding pairs, and they're bent away from each other. A lot of times we draw water as a Lewis structure as if it's linear. And so this, you start to see, especially with the tetrahedral, you start to see that the Lewis structures can be really deceiving. You know, when we draw out water as a Lewis structure, we draw it out as if it's 180 degrees, and it's not. When we draw methane and even ammonia, we draw it as if those bonds are 90 degrees away from each other, and they're actually not. So this is something that becomes really important with tetrahedral molecules because it affects the symmetry of the molecule. And this brings us back to what's going to be soluble and what's not going to be soluble, what's going to be polar and what's not going to be polar. And so if you draw water as if it's a linear molecule like this, right, it would look like you have two dipoles here. And those dipoles look as if they are opposite and equal. So the dipoles look as if they're going to cancel each other out. And that doesn't actually happen with water. If you look at the actual geometry of water, you see you do have two dipoles. They are of equal strength, right? The difference between oxygen and hydrogen is the same on both sides, but they're not equal. They're not symmetrical. They're actually bent. And so if you think of the polarity of this molecule as if you have a tug of war going on, right? And you have ropes that are being tied to the central atom and pulled in either direction, the center of your molecule is going to move, right? If you tie these two ropes to horses and pull it down the road, those horses are going to be able to pull that cart down the road. If you tie two horses together and pull in opposite directions, they're not going to move at all. So when the dipoles cancel each other, that's a non-polar molecule. If the dipoles don't cancel each other, it's a polar molecule. And this is what we see with water. Water is a bent molecule, and that's why it becomes polar and drives all these things around us in the world because it's a polar molecule. And so the Lewis structure versus the VSEPR structure communicate different things, and you have to remember that the Lewis structure does not communicate geometry, and in order to know polarity you have to know geometry. So this is kind of why I love this theory, because as soon as you unlock this theory, all of these other theories really fall into place. You know, we just talked about a tetrahedral molecule, and we went from that to Lewis structures to symmetry to polarity, you know, boom, 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 boom. All of these other ideas really fall into place once you understand the geometry of your molecule. Okay, so we will spend a little time getting back into polarity of molecules in just a second, but let's finish out this VSEPR theory. Let's tie another balloon on. We're going to have 5 regions of electrons that are repelling each other. What kind of angles are going to come out? All right, you predict. I'm going to see if I can tie another balloon on. If anyone wants to hire me for birthday party, I'm available on weekends. Okay. Ugh. So my balloons, I want them to be in a position where they are as far away from each other as possible. Okay, so I come up with something that looks like this. Now, it's kind of a beast of a molecule. Let me push you farther away so you can see it again. Okay, here you go. Kind of a beast of a molecule. So when you're looking at a molecule like this, a good thing to do is try to get as many into the plane as you possibly can. So right away, I see that the yellow and the white can be in a plane with each other up and down. And then if I orient another one like this blue one into the plane as well, then you should be able to see that this purple one comes out of the plane. And the pink one in the back, okay, purple's going out of the plane. The pink one is going to come back into the plane. So let me draw this out for you, and we'll talk about what it's called and what angles are there. All right, so we have one going up in the plane. Here's my central atom, also known as the knot, that's holding all the balloons together. Here, one's going down and one is to the side, right? So that would be like white, yellow, blue. One up, one down, one in the plane to the side. Now the purple is going to come out at you, and the pink one that's in the back somewhere is going to go back into the plane. So purple comes out towards you. Pink goes back in the plane. So these two up and down, and then basically I have 3 around in the plane. So we actually have 2 different angles going on here. We have a 90-degree angle between the top and the bottom and anything in the middle. Notice okay, yellow to blue, 90 degrees. Yellow to purple, 90 degrees. Yellow to pink, 90 degrees. They're all 90 degrees to that yellow balloon. Also, all 90 degrees to the white balloon. But what are they to each other? So if I turn it this way, you may be able to see it a little more clearly. That purple, pink, and blue balloon, what angle are they to each other? Well, they're all in a plane to each other, and there's 3 of them spread equally among that plane. So this angle and this angle and this angle, they're all 120 degrees. So we actually have 2 different angles that happen in this molecule, and this is called a trigonal, and that trigonal is referencing this triangle that happens. And notice if that middle part is a triangle, then you have 2 pyramids. You have a pyramid going up, and you have a similar pyramid going down. So it's called a trigonal bipyramidal. Trigonal bipyramidal. Okay, now in order to have this, notice you need to have a central atom that's attached to how many things? 1, 2, 3, 4, 5. 5 different things. So this is going to be an exception. You're going to have some central atom that's connected to 5 different things. And this has to be, in order for something to hold that many electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whether they're in bonds or lone pairs, it has to be an expanded octet. So we'll go through examples in just a second, but let's finish this and add one last balloon. I'm going to add one more balloon. What kind of angles are going to happen? Here we go. Here's my one last balloon. I'm going to add in, to the amazement. No! I was going to say to the amazement of the whole birthday party, but apparently I'm thinking I'm a little too confident in myself right now. Come on, buddy. You can do it. Oh, we got this. May have made my balloons a little bit too big. Okay. Let's see if I can get this. Oh, yes. Beautiful. Okay, what kind of angles am I dealing with here? Ta-da! Here you go. Here's the beauty that is. Okay, so again, in order to deal with this, it's easiest if we think about what kind of, how many of these things we can get in a plane to each other. So blue and green are the obvious answers. I have one up, one down, and now you can see I have 4 around the middle. Pink, purple, yellow, white, right? So if I orient this to get 2 of them in the plane, the purple and the white are now in a plane. Then the yellow is coming out at you, and the pink in the back is pointing away. Okay, so what kind of angles do I have here? See, little kids think this is so cool. And I get to teach them the VSEPR model without them even knowing. It's sneaky and fun. Sneaky and fun. It's a good combination most of the time. Okay, I have 1 going up, 1, here's my central knot, also known as atom, 1 going down. Remember, friendly reminder, these little lines that I'm drawing, those are the balloons. Those are the electrons that are repelling each other. And so I will have an atom on the end of all my balloons, right? I have 1 going this way, 1 going this way. Let me delete that and start over. 1 up in the plane, 1 down in the plane, 1 to the right, 1 to the left. And then I have 1 coming straight out at me and 1 going back. So in order to draw this, I really have to draw it on an angle. I'm going to draw two coming out and 2 going back. Okay, so there's my molecule. Now, what kind of angles do I have here? Well, these are all in a plane with each other. So if I have 4 in a plane, they're at 90-degree angles. And they're all at 90-degree angles with the stuff going up and down too. And so this is also a 90-degree angle. So all my angles are 90 degrees. Notice pink. Let me orient this. Hold on. Okay. Purple to yellow is going to be 90. Purple to green is going to be 90. And if I orient it this way, so you can see all 4 that are in the plane, blue, pink, green, yellow, all in the plane with each other, they're all perfectly at 90-degree angles to each other. So there you go. All 90-degree angles. Pow. So this one is called kind of a crazy name. Okay, so in order to understand this name, you kind of have to think about it as from that pyramid again. Okay, so if we notice that everything in the plane to each other is going to make a square, right? And then if we go from the top down, we make a pyramid. Notice that. Notice how we make a pyramid that has a base of a square, right? So this pyramid is actually going to have 4 faces on it. And then we have an identical pyramid going to the bottom as well. So we have a pyramid with 4 faces on the top. We have a pyramid with 4 faces on the bottom. So we have 8 faces total if we were to put a sheet of paper on all of this and enclose this shape in, we would have 8 sheets of paper, right? 8 triangles enclosing it in, 8 faces enclosing it in. So we call it an octahedral. This is an octahedral shape. And again, because that central atom there is holding 2, 4, 6, 8, 10, 12 different pairs of electrons, it's going to be an expanded octet. Okay. So there is the VSEPR theory via balloons for you. Let me show it to you via a table. Okay, so this table really summarizes everything we just talked about. We have 2 total electron domains. So that's talking about those regions of repulsion, right? And those regions of repulsion can be a single bond, a double bond, a triple bond, or a lone pair. So 2 electron domains, it's going to be linear. You'll have 2 bonding and no non-bonding. So our example there is carbon dioxide, and these used to spin, but they don't spin anymore. Moving on to 3 total electron domains or 3 total electron regions of repulsion. That's going to be our trigonal planar shape. If we have 3 bonding and no non-bonding, like in boron tetrafluoride, our angle is going to be 120. If we have 2 bonding and 1 non-bonding, so notice this sulfur here has 2 bonding regions, a single bond and a double bond, and a lone pair region, this angle between my 2 bonding regions is going to be less than 120 degrees because that lone pair is going to squeeze those bonding pairs together. Also, sulfur dioxide is going to be an excellent example of a resonance structure. Notice you have a symmetrical structure, but on one side there's a single bond, one side there's a double bond. That's going to be a resonance structure. All right, moving on. We have 4. So 4 electron regions. That's going to be a tetrahedral. And here you see all of our options. 4 bonding, no non-bonding, that'd be methane. It's going to be tetrahedral. You will have your 109.5 degree angles there. If you have 3 bonding and 1 non-bonding, like ammonia, that if I ask you what shape that is, you can answer it's a tetrahedral shape. Sometimes it's also called a trigonal pyramidal shape. So these little names here are like also known as, so they can be a tetrahedral. They can also be known as a trigonal pyramidal. And the angle here is going to be less than 109.5. If we look at water, we have 2 bonding, 2 non-bonding, also known as bent. And the angle between these 2 is going to be less than 109.5, also known as 107 degrees. Okay, if we have 5 bonding pairs, that's going to be known as trigonal bipyramidal, and your angles are going to be 120 and 90. So 120 degrees plus a 90 degree angle. Now that's actually all you need to know for the VSEPR theory with 5 effective regions around it, but there is some more detail here. So you may hear these terms thrown around. You won't be held accountable for these terms. If you have 4 bonding and 1 non-bonding, it becomes a seesaw because you have 2 like bent molecules kind of put together. You have a bent molecule this way. You also have a bent molecule this way, and they're kind of put together like a seesaw. And the angles are going to be less than the angles for a typical trigonal bipyramidal with 5 bonding pairs. If you have 2 lone pairs, 2 non-bonding with 3 bonding, it becomes a T shape. So if you have 1 up and 1 down and 3 around, right? 1, 2, 3. And then this one becomes a lone pair and pushes these 2 down. That's your seesaw shape then, right? Well, if 1 more becomes a lone pair, it actually forces the other 2 into the farthest they can get from each other, giving these 2 the most amount of room possible, and it actually forces it into a T shape. And then if you get 3 non-bonding regions, like down here, the 3 non-bonding regions are going to take up the region with the biggest angle available. So they're going to take up the region with 120 degrees, not the region with 90. And so it actually becomes linear then, because you just have the one pair up and the one pair down. And you can see examples on the side. Those are the 3 examples we talked about for tetrahedral. Here's some examples for trigonobipyramidal. And notice that all of these examples for trigonobipyramidal, they all support an expanded octet. So the central atom is going to be holding more than 8 electrons for all of these. Phosphorus, sulfur, chlorine, xenon. They all have a d orbital available, all in that 4th energy level or higher. So they have access to the 3d orbital, which is why they can have an expanded octet. All right. And lastly, we have the octahedral. You are held accountable for the octahedral arrangement. But again, just like with the trigonobipyramidal, you only really have to know this top one. So 6 bonding pairs, we call it, or 6 electron regions, we call it an octahedral. If all 6 are bonding with no non-bonding, you're going to get 90-degree angles throughout, right? These are going to be the 4 that are in the plane all around it, 2 coming forward, 2 going back. They all have 90 degrees around it, and then they're also 90 degrees to the one going up and the one going down. And then if you have 1 as a non-bonding, it becomes square pyramidal because you still have this square base here that actually gets forced up a little bit. And then you only have 1 here, so it actually forms a pyramidal shape, but only on one half, not both halves. And then if you have 2 bonding pairs, you can think about the one going up disappearing and the one going down disappearing. So you just have the 4 in a plane around the center, and it becomes square planar because they are forced into the plane by these 2 lone pairs. And then notice again, all of these are going to have an expanded octet. Sulfur, bromine, xenon, they're all going to be your central atom, and they're all supporting more than 8 electrons. Okay, so those are all the shapes you have to know. For 6 and 5, you don't have to know these like more detailed versions, but you do need to be able to tell me the number. You need to be able to identify the number of electron regions of repulsion, or they, in this table, they call them electron domains, around your central atom when you're given just the formula. So you have to go formula, draw the Lewis structure, and then identify the number of electron domains around the central atom. And once you know this, you should be able to tell me both the name and the angles that occur inside that molecule. So that's what you should know from the VSEPR molecule. It does take some practice. Tell you what, building it with balloons will probably help you more than anything else. Actually building this model, you could also build it with Play-Doh or just crumple some paper and twist the paper together. That may work also. Balloons are nice though because they automatically repel each other to form these shapes. So they automatically fall into the predicted VSEPR shape. Definitely take some practice, but definitely worth knowing. This is a topic that comes up over and over and over on the test. Every year this comes up. They ask you to draw, name, predict angles for at least one thing, usually in the free response section. So definitely a theory worth knowing. Okay, so we'll pause there. We'll pick it up there next class. We'll do some practice with this. Let me know what questions you have. I'll see you in class.